Today, the topic of this first part of the lesson will be the equations to work out the failure load of a connection with double type fastener. So, as we mentioned on Monday, we said that in order to find out the equation to design the connection with double type fastener, we need to use some equations that are currently in the current Europe 5. And those equations were developed in Scandinavia in 1949 by Johansen. Those equations are based on the lower bound theory, or the lower bound theorem of the plasticity, which basically is assumed that both timber and metal connectors can show a rigid plastic behavior. So basically, one relationship characterized by a vertical line here at the beginning, so like it was rigid without any flexibility, and then a horizontal line showing basically material with infinite ductility. As I said last time, there is a theory called lower bound theorem or static theorem, which basically states that if we have material with this property, so with infinite ductility, and if we are able to find a solution which satisfies equilibrium and not necessarily compatibility, this solution will be a lower limit of the actual failure load. In other words, the idea is that since to solve the actual problem, it would be too complex because it would involve both equilibrium equation and compatibility equation, we can say, okay, we find out, we just use equilibrium, we find out a solution which satisfies equilibrium and not necessarily. Scusate un attimo, ho sentito tutto. Pronto?
Scusami Massimo, ho sbagliato.
Ok, perfetto, grazie. Ciao, scusate. So we'll say that if we find one solution which satisfies equilibrium, we are certain that the actual failure load will be greater than this solution that we found. So in the other way, we can say that our approximate solution is a conservative approximation of the actual failure load. Okay? So this is the basics of this theory, if you want. The only problem, already mentioned yesterday, is that the theorem is based on the hypothesis of ductile behavior, infinite ductile behavior, which is certainly true for steel, but what about timber? What about wood? Is it wood a material with infinite activity? Certainly not. So, we need to make sure that some conditions for wood will be satisfied in order to make sure that this theorem is applicable, because otherwise we would find something which is not reasonable. So, first test that we need to do to understand more about the actual behavior of wood is what we call embedding or embedment strength. So it's an embedding or embedment test, which basically in Italian is prova a rifollamento. Okay, so embedding or embedment in Italian you can translate with rifollamento. So what we do, you see here there is a piece of wood with a dowel crossing the piece of wood. Dowel is basically a steel cylinder, it's like a bolt without the nuts, without the head. So piece of wood, dowel, then with this fork, we apply this fork to a jack, and then we pull, either we press or we pull the dowel with respect to the wood. So in other words, we do a test like this. So this is a piece of wood. here there is the dowel going through. So what we do, we apply a force like this. So here there is this kind of fork. So basically we pull this fork and we pull this piece of wood all together. Okay? So we do what we call an embedment or embedment strength. In this test, when we do in the laboratory, we are going to measure the load, so the value of the applied load, and also we are going to measure this displacement. So how much this dowel is going to displace with respect to the initial position. Okay? So this is a kind of test, embedding strength. The load is applied usually in this way. First, we increase the load monotonically up to 40% of the expected failure load. Then we reduce down to 10%. And then we increase it again up to the failure, the actual failure of the specimen. Okay? Now, in which way, what kind of failure can occur on our specimen? So we have a specimen, campione, where we have wood and a steel dowel. So how can this specimen fail? You can see here all the different failure modes. The first failure mode, A, you see is characterized by a plasticization of the wood at the interface with the steel. So basically the dowel is going to basically compress the wood at the interface with the dowel itself. And for this reason, you can see that the initial hole is going to elongate due to the crushing, the plasticization of the wood at the interface with the dowel. So this kind of failure is actually called, you see here, well, this would be the crushing of wood is actually called embedding. So embedment. It's a failure for embedment. Embedment means la rottura per rifollamento. Okay? Then another type of failure load is the one displayed in B, which is splitting. So in this case, the wood may fail in tension perpendicular to the grain. Because in this region here, we have some tensile stresses, secondary tensile stresses perpendicular to the grain. And since perpendicular to the grain wood is very weak, we can expect that we have this splitting, so this crack, that is going to cut the specimen in two. So this is called splitting. Third way of failure is a failure for shear plant. Now, if you do the same test using steel, so using a steel dowel, could be a steel bolt versus a steel plate. So for the steel, the shear failure would always occur at 45 degrees. So in a specimen made of steel dowel versus a steel plate, the failure would be for shear at 45 degrees. However, in timber this cannot occur because a failure at 45 degrees means that we would have to fail the fiber, as you remember. And failing the fiber is much more complex than failing the matrix. So in this case, if you have a failure for shear, you will have some planes of shear running parallel to the grain. So you would have a failure of the matrix rather than a failure of the grain. Okay? So this is called again shear plant. Then another possibility, if of course the hole is big compared to the size of the plate, then in this case you may have failure of the wood. So wood in tension, parallel to the grain. And last, if you have two dowels, then you can have what is called tear out, which means again failure perpendicular to the grain between the two holes. Okay? So those are all the different failure mechanisms that we may have in this kind of test, which is called M&MoCS test. Now, each of those failure mechanisms is associated with a certain ductility. Now, if we check the load displacement curve that we get with these different failure modes, we will find that the only ductile failure mode is the first. So only when we have failure for embedment, so for crashing of foot perpendicular to the grain, the interface with the steel, only in this case we can get a kind of ductile behavior. So we can get very significant plastic deformation. All the other failure mechanisms are brittle, meaning that as soon as you have a failure, you get immediately a reduction, a significant reduction of the load acting on the specimen. So, this means that if you want to use the lower bound theorem, so if you want to find out as a result of our prediction of the failure load, some equation derived just based on equilibrium, and if we wanted this solution, it's a lower bound of the actual failure load, we need to make sure that the failure will occur in this way. Because if the failure should occur in this other way, then the lower bound theorem is no longer applicable. And this means that the solution that we find is not necessarily a lower bound of the actual failure load. So we are not sure that this is a conservative number. Okay? So this means that, again, we need to make sure that this would be the only failure mechanism occurring in our connection system to be able to apply the Eurocode 5 formula. Here you can see some experimental results. This was a connection between two pieces of wood with a steel plate and two bolts. These specimens were basically applied were loaded in tension. In this case, the research was about fire resistance of this connection, so we were interested in basically trying to predict the fire resistance of this kind of connection. So the idea was, first the specimen was heated in this small furnace, so this is basically a furnace. So the specimen was heated to a certain temperature, for example 200 degrees, for 120 minutes, and then the load was increased up to the specimen failure in order to find out the dependency on the strength of the connection upon the temperature, which is important when we are interested in fire resistance. Those are the curves. So you see the red curve is the curve at 20 degrees, and then as the temperature increases, you get lower load, lower strength, but as you can see also higher ductility. In particular, all these failure modes were characterized by crashing of wood by embedment. Some photos, and here you can see the typical elongated hole. So during the test, you can see, of course, that the timber is going to burn. So this is the color of the char formed on the sides of the wood. And then you can see that the bolt has basically crushed the wood, and the initially circular or cylindrical hole has become an elongated hole because the wood was basically crushing at the interface with the bolt. Again, another enlargement of the hole. In this case, again, as you can see, if you have embedment, you have a failure which is quite ductile. Look at this color. We have certainly good ductility of the material. So in this case, we can certainly apply the lower bound theorem. So, now, how can we ensure that the failure modes, which are brittle, will not occur in our connection? As I said before, we need to make sure that those failure modes will not occur, because otherwise we are not able to use this equation, this Johnson equation. Basically, we do it this way. The regulation provides rules such as minimum spacings and distances from the edges to prevent any failure mode other than traction on board. So in other words, you will see that we have some rules on, for example, the spacing, the minimum spacing between two bolts, two fasteners, and also the minimum distances between the fasteners and the sides of the specimens, because in this way we can prevent the brittle failure modes like splitting and shear, okay, by providing some minimum distances from the bolt. In fact, it's clear that if, for example, you have a specimen where the hole is too close to the end of the specimen, as soon as you apply a load like this you are going to fail basically for splitting perpendicular to the grain. So if you want to prevent the splitting perpendicular to the grain, we need to provide a rule such as, for example, this one, A1 greater than a certain number of diameter of the fastener. So for example, must be greater than 5 times the diameter. Only this way we can ensure that later on we won't get any brittle failure. Okay? So, the results of the failure mode, the results of the embedment tests are then needed to find out the strength of the connection. Particularly, we would say that once we choose the wood specimen, once we choose the fastener, as a result of the embedment strength, we can get what we call embedment or embedding strength. So in Italian this would be la resistenza al rifollamento, FH. So the embedment or embedding strength, resistenza al rifollamento, is a property of the entire system. So it's not a property of the wood or of the dowel, it's a property of the system made by wood and dowel. Okay? So the embedment or embedding strength is given by the ratio between the total applied load and the surface of the wood at the contact with the dowel. Actually, we say the projection of the surface of the wood at the contact with the dowel. So as you can see here, it's F max divided by the diameter of the hole times T, which is the thickness of the wood itself. So basically, if this is the hole, this would be this surface here. This would be D, and this would be T, the thickness of the member. So F max FH, F max divided by B, no, it's actually D times B. And then the strength.
Ma questa è una un fallimento di tipo fragile.
No, this is the failure with the kind of ductile failure, this one. No, okay, no, we need to translate better here. Yes, there is no plasticizations occurs in the fastener. Only the wood. So this is a failure mode where the fastener stays elastic. So the cylinder of the wood, the cylinder of the steel does not plasticize. Only the wood plasticizes at the interface with the steel. So this test, in other words, is carried out by ensuring that the dowel will be stiff enough in order not to plasticize. So the only plasticization will occur here at the interface between the dowel and the wood. Okay, it's clear? Then, since the fastener is made of a plastic material like steel, another failure mode may occur. The steel itself, the steel fastener, may itself plasticize. So rather than having the plasticization of the wood at the interface with the steel, we can also have the plasticization of the dowel itself. So, for this reason, it's very important to know another parameter, which is the yielding moment of the fastener. So we have a fastener which is basically a cylinder, and if we do a bending test on this cylinder, we can find out what is the yielding strength, yielding moment of the fastener itself. So the test, you see, this is a bolt. The test is carried out by carrying out a 4-point bending test where we support the bolt on 2 points. We apply 2 point loads at the third of the length. This is an example. In some specimens, you can see here, you can have a failure characterized by plasticization of the bolt and plasticization of the wood. In other words, the system bolts, the wood plate connected, for example, to a steel plate with a bolt, may fail for coupled plasticization of the wood at the interface with the bolt and plasticization of the bolt itself. Okay? You can also do on a screw like this, you can also do a direct bending test in order to find out the yielding moment of the screw itself. Okay, so now, if we start for the different configurations to write equilibrium equation, we can get to this relationship here, which are the base of the Euro 5, and they are also called European yielding moment. So how do we use this equation? Then we'll see how we can derive this equation. So let's see what the regulation says. Here we are talking about timber to timber and panel to timber connections. Timber to timber means legno-legno, panel to timber, pannello di legno-legno. Okay? So the characteristic load carrying capacity for nails, staples will be graphite. So the staples are like the graphite, like the staple we use for stapling paper, but they are much bigger. So like would be like this size more or less. And they are used also to connect timber with another piece of timber. Okay, it's a kind of U-shaped net if you want. So the characteristic load carrying capacity for nails, staples, bolts, dowels, and screws per shear plane per fastener. So those formulas are always related to the characteristic load carrying capacity per shear plane and per fastener. So if you have 3 fasteners, you need to multiply this value here by 3. If you have 2 shear planes, you need to multiply those values by 2. So here we see fastener is single shear. So fastener is single shear means that you have 2 pieces of wood, and you connect the 2 pieces of wood using a fastener, a dowel. Note that all these equations here are applicable when we talk about double type fastener, meaning fasteners that are inserted in the wood at the right angle. So you see here the fasteners are perpendicular to the direction of the wood itself. We will see later on that there are some fasteners like screws which very often are used inclined, so at 45 degrees. So those equations here applies only when the fasteners are perpendicular to the shear plane, not when they are inclined. So basically, the FVRK, so this means that shear, V is shear, so shear strength, characteristic shear strength is the minimum among 6 different values. So we have 6 different formulas that were derived by considering the equilibrium, so by basically imposing the equilibrium of the forces, and those 6 values, each of those values is associated to a different possible failure mechanism. For example, the first one says that we need to take the embedding strength of the first timber member, so this white element here, and multiplying it by the thickness and by the diameter. So this is a failure for pure embedment, like the one that we were discussing before. So it's a failure where basically we have an elongation of the hole. So this is a timber member, and here we have another timber member. In this case, we have, for example, if we pull this, we have a failure for elongation of the hole here. Oh, sorry, this is wrong. Right now? Yes. So this is a failure for pure crushing of wood in front of the tower. So the 2 timber member, one of the 2 timber members, the thinner one, you see here, is going to fail for embedment. Then we have another failure mechanism, number B, which is similar as before, but in this case, the weakest timber element is not the left one, but the right one. So now you see that plasticization is occurring in the right member of wood. Again, crushing or embedding, but in the right member. Then we have a third failure mechanism, the one indicated by C. In this case, you see that we have crushing or embedment in both timber members, right and left, with inclination of the fastener. So the fastener in some way is going to get inclined in the direction of the pull-out force, is going to crush both timber members. Note that also in this third case, we have no fastener plasticization. Then we have another formula for the mechanism number D. In this case, you see we have embedment in both timber members, and we have also plasticization, so we have plasticization of timber in both members, but we have also plasticization of the dowel with formation of a plastic hinge in the right member. Then the fifth equation is similar to the one before, but this time the plastic hinge is going to fall in the left timber member. And the last one, plasticization of wood in both members and formation of 2 plastic hinges. Okay? So as you can see, we calculate 6 values of loads of strain capacity associated each of those to one of those failure mechanisms, and then for us the load current capacity would be the minimum value, the lowest one. So we have 6 values, we take the minimum one. The minimum one will basically be the strength of the connection, and we will also know what kind of connection will occur. For example, if the minimum value is the third one, so this one, we will know that this will be the actual failure mechanism. Okay? The fact that we can know the actual failure mechanism is very important, particularly when we are going to design a timber connection in seismic area. Because in seismic area we will have to design a connection in order to be dissipative, so to dissipate lots of energy. So in seismic area, the dissipative connection will be the one where we have at least the formation of 1 plastic hinge into the steel tower. So in seismic regions, we want to have plasticization still in order to have significant amount of energy dissipation. If we have only timber crushing, we don't get a lot of energy dissipation, okay? Now this one, there are 4 equations for the case of fastness double shear. So in this case you can see here we have 2 shear planes. So we have, for example, 2 members, the one center one. So we can have 2 failure mechanisms, the G and the H, characterized by only embedding of timber, so only crushing of timber, while failure mode J is characterized by crushing of timber and a formation of 1 plastic inch into the dowel. And failure mechanism K instead is characterized by the formation of 3 plastic inches, one in the middle and one in the 2 members. Now, how can we obtain now this equation? As an example, if you take the first failure mechanism, the simplest one, we simply write equilibrium, as we said before. So we have to consider all the possible different failure mechanisms, and for each failure mechanism, write the equilibrium equation in order to find out the load carrying capacity. For example, if we assume that we have a failure for crushing of the wood in this member here, the only equilibrium equation that we need to write is simply that Rk, which is the characteristic shear strength, is equal to Fh1, embedding strength on timber member number 1, times D times T. We want T1. So this is the equilibrium equation associated with the failure mode A. And of course, if we just swap the first with the second member, we get a second equilibrium equation. So Rk is Fh2k, so embedding strength of member number 2, times T2, thickness of the second member, times T, diameter of the dowel. Okay? Now, another example, failure mode type D. Failure mode type D, if you go back, failure mode type D, as you can see, is characterized by crushing of timber at the interface with the dowel and by 1 plastic inch formation in 1 member. This is failure mode type D. So for failure mode type D, we have to write a more equilibrium equation. So we have first to separate the 2 members across the shear plane. So T2, thickness of member number 2, T1, thickness of member number 1. Once we separate the 2 members, we have to write down the unknowns. So Rk will be the shear force transmitted here on the shear plane. It is our unknown. Also the bending moment in the fastener at this section is unknown. And then we will have a plastic inch formation at a certain distance A from the shear plane. And as you can see here, we will have the inversion of the deformation in a section at a certain distance C from the shear plane. So in the end we have 4 unknowns. A, the position of the plastic inch, C, Rk, which is actually the load carrying capacity that we are interested, and M, bending moment in this cross section. So in order to find out the solution, we need to solve this system of 4 equations in 4 unknowns. First equation, we know that at the level of the plastic inch here, the shear must be equal to 0. So the plastic inch, the shear is equal to 0. So we can write down that for the equilibrium of this piece of pin here, Rk minus, here we assume that the we have a crushing pull, so minus FH2K, which is the bending strength, times T times A, where A is the distance, equal to 0. So RK equal to this FH2K times T times A. Then we can write the moment equilibrium in the shear plane, so in this point here. So in this point here we have M, the unknown bending moment in the dowel, minus, because this is the opposite rotation, minus MYK, which is the characteristic bending strength of the dowel, plus the moment of this system of forces. So FH2 times D times A times A divided by 2. So moment equilibrium of the shear plane. Then looking at the part of the specimen underneath, we have the force equilibrium of this member here. So RK minus FH1 times C times D plus FH1 times D times T1 minus C. So if we rewrite again this equation, we will find out that RK is FH1K times D times 2C minus T1, equilibrium of forces. And then last but not least, moment equilibrium in the shear plane. So moment equilibrium in this point here. So here we can write that M equal to this expression here. So we have to find out this RK has a lever arm equal to 0, so it's got no moment with respect to here, but we have FH1 times C times D times C divided by 2, and then FH1 here times D times T1 minus C times the distance from here, which will be T1 plus C divided by 2. So in other words, as you can see, in this method, we try to consider different failure modes possibilities. For each failure mode, we write the condition of equilibrium. We solve the system. If we solve this system, particularly if you assume that beta is the ratio between the two bending strengths of the two material, so we make this assumption, we solve the system for the equilibrium equation, the shear strength that we obtain is given by this formula here. Okay? So this is the formula that provides us the strength using the lower bound theorem. If you compare this equation with the equation in Eurocode 5, you will find that there are some additional factors. So for example, we have this factor 1.05 multiplying this term, another 1.05 multiplying the second term, and the last one, the factor 1.15. Where do these factors come from? These factors are a kind of adjustment factors that have been proposed by Eurocode in order to make those results comparable with the experimental tests. So they performed lots of experimental tests and they found out that without this factor 1.05, 1.15, the test would have been probably overestimated, would be largely underestimated by the numerical prediction, by this analytical prediction. Another thing that we can see is that in some of these failure modes, to this time that have been derived using the equation, has been one other additional term has been added. So you see that there is for failure mode C, D, E, and F. To this term here, for example, before we derived this term here, RK, but this RK is only one part of the formula that you find in the Eurocode. In the Eurocode, you find this part Then you find the coefficient 1.05, and then you find, you see this, plus FAX RK divided by 4. So this additional term is called rho effect, effetto corda in Italian. What is the rho effect? The rho effect takes into consideration an important effect related to the fact that in some fasteners there is also a withdrawal strength. So the fasteners have some resistance to the extraction, resistenza all'estrazione, and as such, when we load the specimen, we can get some support from friction. Now you can see better with this figure here. Now this is a cross section of a timber to timber connection using dowel. So in this case, you see the idea is I push down the central member, and then you can see I can get a plasticization. I can get some crushing output here at the interface with the steel, and also crushing output at the interface here with the always with the steel in the book, with the other specimen. Now, if you think about having a dowel with these plates, so those plates, those washers, basically prevent these dowels from moving inwards in the specimen itself. Suppose that you had a dowel without washers. So this is the specimen, the inner part of the specimen, this is the lateral. And this is the dowel, initially straight, without any washer again. If I push down the specimen, what kind of deformation I can expect? Assuming that there would be a plasticization of the dowel in the central part. I can expect this is going down, and this is going to deform this way. Right? Is it reasonable? Now, once we get to large displacement, like here, what kind of displacement or deformation can you expect in the dowel itself? So the dowel is going to deform in this way, but as you can see, the length is much higher than the initial length. Okay? If you look at the deformed length of the dowel, since we have a large displacement, this length is much larger than the initial length. Meaning that this dowel, if this dowel is smooth, doesn't have any washer here, and doesn't have any thread inside, this dowel, to stay in this configuration here, like it was at the beginning, it should elongate quite a lot. So this is quite a significant elongation. So either the dowel elongates itself, or the easiest thing that may happen in this case here is that simply the head of the dowel will keep its total length constant, and the head of the dowel will go inside here. So in the end, you will have that the length will be the same, but the dowel is going to move inside in this case. Okay? So if this is going to happen, we could say that here, since the dowel is smooth, here there is no significant friction being transferred between the dowel and the loop itself. So in the end, we will have that the stress here will only be a shear stress. So there won't be any significant compression of the plates. Okay? Because the dowel itself is going to move inwards. And since it doesn't have threads, so filetti, it's not going to impose any compression in the two pieces of wood. Now, if we redo the same test, but using, you see, these plates here, what is going to change here? So if this dowel has now two plates here, and we start loading, and then the dowel forms this plastic hinge. What can we expect in this case? As a difference to the case that we have just discussed. The length, yes, the length of the dowel would like to increase. Can this length freely increase? No. So if this dowel increases its length, what's going to happen then? To increase its length, what must happen in this dowel? No? So the dowel initially, let's say the dowel is 10 centimeters long. In this configuration here, to get to this configuration, the dowel should become 11 centimeters long. So in order to stretch this dowel by 1 centimeter, 10%, what do I need to do? Do I need to apply a tensile force? Who is going to apply a tensile force here on this dowel? The washers, exactly, the washers. So the washers, if you want, the dowel itself is going to stretch by 1 centimeter. So why is it going to stretch? It's going to stretch. Before it didn't stretch at all because it could go inside freely. But now, in some way, we fixed this point here. So in the end, while before, let's put it this way, before we had a sort of scheme like this. Okay? So I apply this load, this is going to plasticize, and of course we are going to have something like this. And this moves it inwards. Okay? This was the case of the dowel without the plates. Okay? Now instead, if I put this two member here, then I have a scheme like this. This one becomes a fixed point. This becomes a fixed point. So when I apply this central load, I can get something like this. But of course, like if I had a row, in order to get to the equilibrium, here, this must go in tension because I fixed the lateral point, because I connected the dowel with the washer. Okay? So now, of course, I can stretch the dowel. I can increase its length by 1 centimeter by 10%, but of course, because of this 10%, I get a tensile force, quite significant. Okay? Now, this tensile force, who is going to provide me with this tensile force? So this pin here, who is in the reality in our system?
A compression force.
No, this is a tensile force. Yes, okay.
What does it
Yes.
plate is a compression force.
Exactly. So, but this restraint here is provided by which element? So here, this one corresponds to which element here?
With the plate.
With the plate. So the plate provides this restraint, and for the principle that at each force you get the same reaction, the plate itself, if now I study the equilibrium of the plate, so here, this is a tensile force, and the plate itself will have to distribute a number of compression force at the interface with the wood itself. So in the end, if you want, this system induces on the specimen one force which is applied in this way on the specimen itself. So this red force here is a compression force equal and contrary to the tensile force that I get in the towel, and this compression force will be applied from the washer directly to the wood itself. Okay? It's clear? Now, what is the effect of this compression force on the specimen? Bearing. So this compression force may plasticize the wood itself, but as you can see here, to avoid this, the washer must be quite big, not like the washers that we use for steel construction. Those washers here are 2 or 3 times larger to avoid bearing, to avoid this indentation of the wood. Now, what is the other effect on the total spacing of this compression force? This compression force, as you can see, will have a horizontal component. This horizontal component is going to compress this timber on this other timber here. But here, on the slipping surface, are the two surfaces free to slip? Well, if the apply compression force, we have always a phenomenon called friction. We have friction. So we have a friction at the interface you see between these two metals. Did we have friction here before if we had no steel plates? Could we count on friction here? No, because we didn't have any compression force. So no compression, no friction. Instead, in this case, as you can see here, we have a compression force, which could be fairly high. Particularly if you want to, if you have this kind of deformation here, we're talking about quite a significant stretch. So quite a strong force, compression force. So compression force means also quite a significant friction. And this friction, you see that knee is the friction coefficient times this compression force. This friction is favorable or unfavorable to the resistance. So it opposes to the strength in some way. It's positive for us to have this friction or not. Positive, because this increases significant the strength. So in this case, we said no friction, so all the strength is coming basically from the dowel itself and the interface with the wood at the interface, while instead in this case, we have also contribution from the friction. This is why, this is called, as I said, the rope effect. This is why, here is another interesting image. Here we have a nail, we have a head. The nail is smooth. So if you connect a nail with here the wood, you see that once you get this deformation, the nail is going to move. You see that the point is no longer here. So as soon as I increase the force, this nail is going to move down. So in this point will move more and more leftwards. In this case, do we have a significant rope effect? What do you think? We have a little bit because there is this head here. So you see the head doesn't go inside. But this nail is smooth, and after a little bit of while, this nail will be able to move outwards. And as it moves outwards, then immediately we lose all the friction. So smooth nails will not get a lot of this rope effect. What would be the difference between a smooth nail and a screw, in your opinion? If I had a screw here with all the threads, is the screw free to come outside? No, because there are the threads which in some way are cannot move freely from the timber unless they broke the timber. Okay? So for a screw, if we replace the nail with a screw, for sure we will have a higher rope effect. If we have a smooth dowel, like here, without the heads, do we have any rope effect? With the dowel, without the washers? Minimum. Hardly anything, I would say. If we have a bolt, this is the case of the bolts, if we have this plate, this washer, if we have a bolt, are we going to have this rope effect or not? With the bolt? With the washers, yes. Yes. Okay. So now we understand better why, if you go back to see what the Eurocode 5 writes, you see here, now let's try to see what's there. In the expression 8.6, 8.7, the first term on the right hand side is the node carrying capacity according to the Johansen yield theory. So, if we go back, this first term, you see all these first terms are the one that we get by writing the equilibrium equation. The one we call Johansen parameters. Okay? Then it is written for the modes C, D, E, and F, we have this additional contribution called rope effect. The second term, F, A, X, R, K divided by 4 is the contribution from the rope effect. Now, why F, A, X, R, K divided by 4? We said before that this additional contribution to the strength that we can add the normal strength is basically a friction coefficient times an axial force. Okay? Now this axial force, what could be the highest value of the axial force that we can get along this surface? Well, the highest value of this axial force will be the actual tensile strength of the dowel itself. Okay? It's what we call in English withdrawal resistance, which is kind of tensile strength. Resistenza all'estrazione. Okay? So, this maximum will be equal to what we call FAXRK, which means characteristic withdrawal resistance of the fastener. So the strength of the fastener, the force that I need to apply to the fastener to take it outside. Okay? So for example, this is one member, this is another member here. I put one screw here. FAXRK, characteristic withdrawal strength, is the value of the force that I need to apply on the screws to withdraw the screws, to take the screws out. Okay? Obviously, I cannot get a higher force perpendicular to the brain higher than this value here. Because as soon as I get this value here, I get either the failure of the screw in tension or the withdrawal of the screw. So this will be the maximum value. Okay? Now, this value must be multiplied by μ, which is the friction coefficient. Now, if you look at the Johansen equation, can you find here? Let's go back. Can you find in this term here a friction coefficient? So FAXRK, we said this is the perpendicular force. What is the friction coefficient? If you look at 1 force, 1 divided by force equals 0.25. 0.25 is more or less the friction coefficient. So it's kind of a conservative estimation of the friction coefficient between wood and wood. The mean value of the friction coefficient between wood and wood is around 0.4. Here, conservatively, they will use the characteristic value, which is 0.25, namely 1/4. So this 1/4 of FAXRK divided by 4 is basically μ times FAXRK. Okay? So this is what is called rope effect. Now again, let's go back to the Eurocode 5. the contribution of the load carrying capacity due to the rope effect should be limited to the following percentages of the axial part. So round nails, do you remember before we were talking about nails? Did the nails provide lots of rope effect? We said no, because they are small. In fact, we can see that maximum, this rope effect is 15% of the other term, no more than 15%. Square nails, 25%. Other nails 50%. You see the best, so the best results we can get if you use the screws. Because the screws is, I would say, intimately connected with the wood itself. So the screw cannot move freely. So with the screw, you get up to 100%. So if the answer equation is 5 kilonewton, you can add to this 5 kilonewton up to 5 kilonewton withdrawal resistance of rope effect. Bolts 25%. And dowels, nothing, because the dowels are free to move inside, so we don't get any compression if you use the dowel. Okay? So, in the end, now you understand why in this equation there are the first term, you answer term, plus this rope effect. And just keep in mind that this rope effect, to calculate the rope effect, you need to calculate the withdrawal capacity of your nail screws. Then you need to divide it by 4, and you need to compare this value here with the value of the first term, depending on the type of fastener. If the fastener is dowel, of course, you can't add anything. If it's nail, you can add up to 50 or 25% of the first term. Of course, if you don't know the withdrawal capacity of your fastener, then the contribution from the rope effect should be taken as 0, so you just ignore it. Okay, is it clear about this concept? Okay, then of course, when designing timber structure, after timber to timber connection, we have very often also steel to timber connection, because very often it's very convenient also in order to reduce the size of our members to use steel plates rather than timber plates. So, steel to timber connections, have a look at the regulation. Characteristic load carrying capacity for steel to timber connection depends on the thickness of the steel plates. So it's not the same to have a very shallow steel plate or a very thick steel plate. The value mechanism may be different. So steel plates of thickness less than or equal to 0.5 D are classified as thin plates. So, what does it mean? For example, this is a timber to steel connection. So this is a bolt, for example. Diameter of the bolt, and this is the thickness of the steel. So, you see that if T is less than or equal to 0.5 D, then we define the steel as a thin plate. If T is greater than D, then we can define this as a thick plate. Okay? And if we have a value in between, which sometimes may happen, then the regulations say, okay, you do two calculations. First use the formula for the thin plates, then use the formula for the thick plates, and then you do the interpolation. Interpolation, of course, on the thickness, on the value of the thickness. So, for example, in this case, you find on the value of the diameter in this case, but the thickness is the same. So you use the same formula with this condition here, the same formula with this. If your diameter is 0.75, you just take the average. If your diameter is 0.9d, if you go 0.75d, you take the average. If it's 0.9d, you take a value closer to this value here. We just do an interpolation, linear interpolation of the value of the diameter, not the thickness. Okay, it's clear? Now, another important thing, the tolerance on hole diameter less than 0.2, 0.1d. What is the tolerance of the hole diameter? When you have a hole diameter, you can't have, also in steel structure, you can't have a diameter of the hole when you put the bolt exactly the same as the diameter of the bolt, because then you have always some small mistake, some small error by building your structure. Then you wouldn't be able to put the bolt through the hole. So you have always to have a small tolerance. So the tolerance in this case, you see, must be less than 0.1d. So if you have a diameter of 10 millimeter, 0.1d is 1 millimeter. So the hole should not be more than 0.1d, the diameter of the bolt itself. Okay? You need to keep this tolerance to a minimum. So, if you have a thin steel plate in single shear, so single shear in this case here, timber and wood, then we can have two failure modes. One failure mode is pure crushing of the dowel into the wood, and the second failure mode is crushing with plastic hinge formation in the wood, all over the fastening. This is a thin steel plate. For a thick steel plate, we have a three failure mode. Pure, here we have a pure crushing of wood. Then we have crushing of wood, a formation of one plastic hinge. And then we have plasticization of wood, the formation of two plastic hinges. And those are the formula. Another type of connection could be instead one single steel plate with two timber members. Also here we can have crushing of wood, formation of one plastic hinge into the dowel, the formation of three plastic hinges in the third failure mode. Last, if you have like in this situation here, two steel plates outside of wood, you may have first failure mechanism is basically the dowel stays straight, so we have plasticization of the wood at the interface with the dowel. A second failure mechanism, two plastic hinge formation inside. This was if we have a thin steel plate. If we have a thick steel plate, then we can have also, you see, this failure mode M, which is basically characterized by four plastic hinge mechanisms. So we have a formation of four plastic hinges instead of only two, like in the case of thin steel plates. So the characteristic strength of one connection can be done by performing this kind of test in the laboratory. So here we have one inner central member, two lateral members. Here you have a number of nails, as you can see here. We apply a load on the top of the space and we measure, you see with this potentiometer, we measure the displacement, what we call joint slip. The tests usually are done in this way. we load up to 40% of the failure load, then we download to 10%, and then we load again the failure. If we compare the load deformation or load slip curves for different type of specimen, so different type of fastener, you see, in the case of bolt, we have this initial deflection, reduced stiffness due to the hole slab of the bolt in the hole, so due to this difference in diameter between the hole of the bolt and the diameter of the bolt itself. And then you have nail, dowel, and bolts with toothed plates. As you can see, so basically the bolted connection, due to this difference in diameter, due to this, what we call in Italian, gioco for bullone, we have initially a larger flexibility, and then at the end we get to the same curve as in the case of the bolt without this tolerance. Now, in terms of fasteners, we take a look to different types of fasteners. We start from nails, which are for sure one of the most common fasteners used when we build the timber structures. So nails, of course, in Italian, chiodi. Nails have usually diameter quite small. For this reason, we say that the nails part the fibers. So once you insert one nail into the wood, in general, this nail is not going to break the wood fiber. It's rather going to pull apart the fiber themselves. So it doesn't break the fiber, it just finds its way down by pulling or by pushing apart the fiber. So what we said, the nails part fiber, they don't break the fiber itself, which is good. Because every time we break a fiber, we have a reduction in strength. Instead, if the nail doesn't break the fiber, for sure, it's a better result. Those are small diameter fasteners, so those are very flexible to use it. The force are transferred mostly by bearing and friction. And then we have many small fasteners. So low load per unit area over large area. So little stress concentration. In other words, once we use a nail connection, we have a connection which is more distributed, meaning that we have low load per unit area, little stress concentration. Instead, when we use the bolts, we have a lot of stress concentration around the bolts, so we have less, if you want, more discontinuity in terms of stress distributions. The screws behave and design in a similar fashion to nails for diameter less than 6 mm. So if we have screws less than 6 mm diameters, we basically design the screws like nails. Instead, if we have screws with more than 6 mm diameter, then we need to design the screws as a bolts. But we will see that the bolts have some other rules. In general, the screws are more expensive to install because usually the nails are bent into the timber. So usually, when we use a nail connection, we don't go there with a hammer like in the old days. We have a kind of nail gun. With this gun, you basically bend the nail. So it's very fast, of course. Of course, with this kind of nail gun, you need to be a bit careful because it's a light weapon, you can imagine. So, and also the nail gun works for small diameter nails. If you have a nail of 8 mm, you need more than a gun, you need something much bigger that is not so big. So in the end, you can bend the nails up to small diameter, 3 mm. 3 mm, you bend the nails. Otherwise, it's more convenient to use, otherwise you need to do pre-hole, to do the pre-hole, and then you can insert the nail. So the nails are very convenient for small diameter. Otherwise, are more convenient the screws, because the screws, if you remember, they have we mentioned last time, the screws can be self-drilled. So the screws can find their way You can just screw without the need to cut another pre-bond. So, see?
But in which direction I fix the nails if I don't have to break the fibers?
No, usually the nails, you can put the nails in any direction. The idea is that since they have very small diameter and they have this point done in this way, once you insert, for example, the wood, suppose that your wood is oriented this way. This one, they just part the fiber, so they just enlarge the fiber, and they don't break directly the fiber. Well, instead, when you use the self-tapping screw, this is going to cut the fiber. It's going to cut and takes outside the shaping. Okay? Which one? The fiber. Il trucciolo. Sì. No, il trucciolo è la punta stessa che lo tira via. Lo taglia e poi lo fa uscire. Non deve tirarlo via lei. Quando lei inserisce il... No, allora, se la vita ha un diametro grande, bisogna fare un preforo a 80% del diametro, no? Con un trapano, e dopodiché si inserisce la vita con l'avvitatore. Se la vita è sotto i 6 mm, anche fino a 8 mm, le viti autoperforanti hanno una punta particolare che taglia il trucciolo e lo fa uscire, cioè praticamente lei non è che lo deve fare, lei come con l'avvitatore vede il trucciolo che viene fuori. Poi è chiaro che se lei prova ad avvitare queste viti autoperforanti di diametro molto più grande, a quel punto deve avere degli avvitatori molto potenti, no? E spesso magari li brucia, no? Per cui soprattutto sono viti lunghe, per cui là bisogna fare comunque il perforo. Okay, now for the nails we need to define the thickness of the timber members that can then be used in the Johansen equation. If you remember the Johansen equation, we have, for example, for two timber members, we have the thickness of one timber member, T1, and the thickness of the other one, T2. Now, as you can see here, T1 and T2 are not the thickness of the total timber member. T1 is the thickness of the total timber member on the left, but T2 is not the total thickness of the timber member, it's only the thickness of the point of the nail within the member. So this value here shall be put into the Johansen equation to find out the value. Similar here, in this case you see T2 is this big member here, and T1 is the thickness, the length of the point of the nail of screws in the first member. Okay? So, the design inequality in this case would be QDI, which is the strength demand, the shear strength demand on the nail, on the fastener, the one that we calculate, if you remember, like we saw last on Monday, considering, for example, the total bending moment transferred by the connection, or the total shear force divided by the number of nails. So this one shall be less than or equal to the load carrying capacity of a single nail. How can I calculate the load carrying capacity of a single nail? Will be if the nails or screws they are aligned parallel to the grain. So if this is the member, this is the grain direction. If I have n nails along parallel to the grain, I need to remember that I cannot just multiply the strength of a single nail times n. You need to consider that since they are all aligned parallel to the grain, there will be an interaction. So the total load carrying capacity will be less than n times the load carrying capacity of a single nail. So you need to use this NEF, effective number of fasteners. So if I now refer to only a value of the shear demand in a single nail, So if this is our Q di, what I need to do, Q di shall be less than NEF, effective number of nails parallel to the grain, divided by the total number of nails. Then I need to multiply by the number of shield planes. So if you remember, which number of shield planes do we have in this situation here? 1. How many shield planes do we have in this situation here? 2. Because you see the fastener is crossed by 1 shield plane here, 1 shield plane. So here we need to multiply by NS. NS 2 here, 1 here. Times FVRD. FVRD is the design shear strength of a single nail, which is K mod times FVRK divided by gamma. So this is the normal, where FVRK is the characteristic shear resistance of a double type fastener calculated with the Johansson equation, the one that we saw before, okay, the Euro code 5. This is very important. We were discussing before about pre-drilling. When do I need to pre-drill the timber? Timber should be pre-drilled, so devo preforarlo, when the characteristic density of the timber is greater than 500 kg per cubic meter. So if you have a hardwood, it's much more difficult to screw one screw inside than if you have a softwood. You risk to burn your driller in a hardwood, because it's much more resistant, much more dense, you see. So in this case you need to pre-drill. And also you see when the diameter T of the nail exceeds 6 mm. So above 6 mm, first I need to pre-drill to 80% of the diameter of the nail, and then I can insert the nail itself. So, in order to use the Johansson equation, I need to calculate the yield strength or yield moment of the fastener. Now, for smooth nails, we can use this formula, this empirical formulation, to calculate the yield bending moment. Note that those formulas are semi-empirical. So, strictly speaking, the yield bending moment of one nail, how should it be calculated? For example, using the plasticity theory. So the plastic moment of an nail, your opinion, how should be calculated? So you have of both. You have a circular cross-section, and you need to calculate the yield bending moment. So this is the moment leading to the full plasticity of this circular cross-section. So what is called MYRK should be equal to what? WP, exactly. So section modulus of the circular cross-section times the yielding strength, or times what they call there, it's FU. WP is equal to what? Would be a certain coefficient that we don't know now, but this coefficient times what? What you can expect to have here? No. In terms, not in terms of WE, in terms of basic geometrical property. What would be? Sorry? What is A? No. We are talking about the section modulus. Not A. Diameter, modulo di resistenza. Modulo di resistenza. So diameter right? What is the section modulus of a rectangle, for example? B D squared divided by a number. 6, the elastic one, 4, the elastic one. Okay, and just forget about the number. So here will be k times what? Q. D must be to the power of 3. So in the end, this MYRK should be something like k, a number, 1 divided by 12, 1 divided by, I don't know, 1 divided by 60, I don't know now the number, to find out, times dq times fu, right? In fact, this is dimensionally correct, because fu is megapascal, Newton per square millimeter, so Newton per square millimeter times dq is millimeter cube, so Newton per millimeter is a bending moment. Okay? Now, if you look at this formula, you see it's a number times fu, and this is fine, and then it's d to the power of 2.8. What is the meaning of this? Basically, what they did lots of experimental tests. They tested thousands of nails in Germany. They found some clouds of points, and then they tried to find some interpolating curve. And this interpolating curve had this exponent of 2.8, while instead physically we should have found 3. So there is a criticism about this extensive use of empirical equations in Europe 5. Very often you find equations like this which are meaningless in terms of dimension. Of course, they fit well the results, but of course this is a semi-empirical. In fact, now in the new revision of the Europe 5, all these semi-empirical, most of these semi-empirical formula will be changed and will be put in this form here, which is the right one. So it will be a coefficient k, perhaps will be 0.3, will be 0.57 or something like this, times d to the power of 3, which what should be that, times fu. It will be much more logical and easy to use for the user. Because the user here does not understand why there is a d to the power of 2.8. If you show a formula like this to Professor Longo, he would just become crazy and say, well, what's the point of doing this kind of thing? There's no physical, no meaning, it's meaningless. It doesn't have any connection with the actual science, if you want. And this is true, it's partially true. The only thing is that they did this because they found out that this way there was a better fit with experimental results. But of course, for the designer, it's not nice. So now this will be changed. But of course, to find it, we have to wait until 2024, not 25, so you will have time to wait ahead of you before the new Eurocode with the new formula will be released. Okay? For the time being, we need to use this equation here. Good. Now, another quantity that we need is the embedding strength. Embedding strength, you remember, is needed again in this Johansen equation. Now, for the embedding strength, we have again semi-empirical formulation. You see, embedding strength of a nail without a pre-drill hole is a number times characteristic density of wood times the diameter to the power of minus 0.3. Again, formula, empirical equation obtained by checking, basically by trying to fit some experimental results carried out on, I would say, thousands of specimens. Okay? Typically in Germany, they do this way. In Germany, they test their good laboratory, good investment in research rather than in tangents that you have recently in Italy. We have more investment in corruption. So the enterprises invest more money. This was taught by, I think, the Canton or some of them. In Italy, the enterprises invest more money in corruption than in research. In Germany, there is a bit less corruption, more research. In Germany, they do this experimental campaign where they test 10,000, they do 10,000 tests, and then they find out this relationship in order to fit as they can the best. No, I can't speak in Italian because, sorry for that. I know there would be finally, you say finally, it relax a little bit, but this is not the case. So, as I was saying before, they test dots, they do lots of tests, and then they fit these experimental results with this kind of approximate relationship. Okay? So, again, here, it's important to make you to notice that we have the use of the characteristic density. If you remember, once you choose the strength class, you have the value of the characteristic density, the value of the mean density. So for embedding strength, you need to use the characteristic value, the density. Now, just a reminder, once we go to check a complex connection like this with several nails, since for nails, as you can see, the embedding strength is independent of the direction of the force. So for a nail, the embedding strength is the same in the direction perpendicular to the grain and also in the direction parallel to the grain. It's always the same. There is no difference in the two directions. Meaning that once we have to check a complex joint like this, what we can do, we can just refer directly to the most stressed nail. So for example, in this case, we know from the last day that the most stressed nail is this one here, where you have a maximum strength demand. So in this nail here, we can make our ultimate limit state design. So we go to control here to compare the strength demand with the capacity. We don't need to check any other nail because we know that FBRK will be the same for all nails because it's independent on the direction of the yellow force. Okay, now, another thing that we need to calculate is the effective number of nails. We said before, if we put more nails on the same line, in general, we need to reduce the number of nails. We need to take a reduced number of nails. So, let's see what they say, what the regulation says. For one row of n nails parallel to the grain, unless the nails of that row are staggered perpendicular to the grain by at least 1d. What does it mean? It means that if I see here, if I put the nails staggered, so rather than all a line, but I stagger them by 1d. So the distance perpendicular to the grain is 1d between this and this. So I alternate the nails in this way. If I do it this way, I don't need to apply any reduction because basically they are not a line. They are a line 2 by 2, but then the distance is very big. Okay, so if I do this staggering, then I can use in my verification the actual number of nails. But if I don't do this, then I need to use this relationship here. The effective number of nails is n, actual number of nails times KEL. KEF. What is KEF? Is an exponent which value depends on the spacing of the nail. So you can see here that, for example, if I use non-pre-drilled nails, if the spacing between the nails is more than 14 diameter, then I have no interaction between the nails. So I can basically consider the nails as if they were independent. And so in my formula we use n. However, if I reduce this spacing from 14 diameter, okay, let's understand what is 14 diameter. For example, if I'm using a 3 mm nail, 3 mm diameter nail, which is quite common. So 3 times 14, we're talking about 42 millimeters. So we're talking about, if I have done the right calculation, if I use a spacing between this 3 mm nail of at least 14 times 3, 42, if I use a spacing of at least 42, so 4 centimeter 2 millimeter, then, which is not a lot, I think, in this case, basically, I have no interaction between the nails. So I can use the actual number of nails. If I reduce this space from 42 millimeter to 30 millimeter, so for a 3 millimeter diameter nail, I use 30 millimeter spaces, so 3 centimeter, then you see I need to use, for a non-pre-drilled nail, I need to use a effective number of nails given by the number of nails to the power of 0.85. If I reduce down to 7 diameter, so 7 times 3 is 21 millimeter. If the space is reduced to 21 millimeter, so 2 centimeter, in this case, I need to calculate the number of nails to the power of 0.7. I cannot reduce the spacing less than 70, so less than 21 millimeter, because if I was to do so, then I will get problem like splitting. Remember before we said that we need to take some minimum spacing and distance of the nails from the ball, because otherwise some of those brittle failure modes, like splitting, may occur. So the regulation says we can't have a smaller specimen than 7 diameter, because otherwise we will get splitting, and then you answer the equation won't provide a conservative estimation of the actual failure. Okay? And then these are the minimum spacing and edge and distances for nails. So let's try to understand what does it mean. And what's the comparison, for example, with the spacing that you use for steel structure. Now, you haven't studied steel structures yet, I guess. Because you have to do it later. So, anyway, let's have a small comparison. So, consider, for example, the case of a 3 millimeter nail, so D equal to 3 millimeter, so very small nail, which is used without pre-drill hole, so it is bent inside in the wood. So used without pre-drill hole in normal softwood, so spruce, meaning density, characteristic density of less than 420 kilogram per cubic meter. So this column here should be applied in our case. So let's see what kind of spacing we should be using. So this is our timber member. So the nails are this way. So A1 is the minimum spacing between the nails. A1. So A1 and A2 is the spacing. So this is the grain, and this is A2, the spacing across the grain. And then, if you have, for example, a post like this, oriented in this direction, we have A3 key, so this would be A3 key, and A40. This one would be A40, A40. So, go back to the table that we saw before. Spacing A1, parallel to the grain. So the diameter less than 5 millimeter, this is our case because the diameter is 3 millimeter. So 5 plus 5 cos half D. Alpha, if we go back, alpha, as you can see here, is the angle between the force on the nail and the direction of the grain. So in this case, alpha equal to 0 degrees. Because you see that we have assumed that the force on the nail is parallel to the grain. Okay? So let's go to C. D, A1. So A1 shall be greater than or equal to 5 plus 5 cos alpha D. Now, alpha equal to 0 degrees, cos of the cosine of 0 degree equal 1. So we get, you see, 10, here probably a parenthesis is missing, yeah, 10 dB. So A1, the spacing between the nails, shall be at least 10 times the diameter, which means 10 times 3, 30 millimeter. A2, spacing perpendicular this time in the other direction, greater than 5t. 5 times 3, 15 millimeter. Then we have A3t, shall be at least 10 plus 5 cos alpha. 10 plus 5 cos alpha times d. So 15d. 15 times 3 is 45 millimeter. And then we have A4t. A4t. 5 plus 2 sin alpha d. 5 plus 2 sin alpha d. So, sin alpha is 0, in this case. Sin of 0 is 0, so 5d. Meaning, 5 times 3, 15 millimeter. Okay? So, as you can see, we are talking about spacing, 10 diameter, 15 diameter, well, let's say spacing A1, 10 diameter and 5 diameter, and the end distance is 15 diameter, 5 diameter. Now, when you're going to study steel design, you will find that for steel, those limits are much less. So for steel, for a bolted connection, in terms of minimum spacing, we are talking about 3 times the diameter. So not like in our case. In our case, we are talking about 10. For steel is 3. And distances, in this case, we are talking about 15 diameters. For steel is something like 1.5. So this limitation on the spacings and end distances are much more severe in timber compared to steel. Why is that? Because in steel connection we have steel to steel. So the steel bolt and the steel plate. Here we are talking about steel bolt timber member, which is much softer and much weaker compared to steel. So for this reason, in order to avoid splitting and all this kind of shear failure, we have to be more stringent in terms of limitation on spacing and so on. Of course, if you are using panel to timber connection, so if you are connecting the nail not to a normal wood member, but to a wood-based panel, like for example a steel plywood or plywood, which are more isotropic, better properties, in this case, we can multiply this values here by 0.85. So we can reduce, we can increase by 15% the minimum distances. For plywood, for example, the characteristic embedding strength is calculated with this, again, semi-empirical relationship, 0.11 characteristic density times the diameter to the power of minus 0. Okay, now, to close this lesson about nails, we draw a strength. So far we have been talking about shear strength. What about withdrawal strength? So once we put the nails inside, what is the value of the force that we need to apply on the nail to extract the nail, so to withdraw the nail? This withdrawal resistance is important because we may need this quantity to predict what we call the rope effect in the Johansen equation, but also a nail could be subjective not only to shear but also to withdrawal force. So, you see here the axial characteristic, or the characteristic withdrawal capacity of the nail is given by these two relationships here. The minimum of these two relationships here. So what kind of failure modes concern those kind of relationships here? So you see here, this is a nail connecting one member with another. Now, we can have two different failure mechanisms. First failure mechanism is when we pull this nail, and this nail stand outside from the second member. So basically we have we have to win the friction between this point and the member itself. And this is Fxk, so characteristic point side withdrawal strength. So this is the failure of the point side of the nail. So characteristic point side withdrawal strength times the diameter times the length of the point side. Or second possibility is that we have a crushing of the wood without underneath the head. So in other words, this failure here could be either because I pulled down the nail, so basically I put far away this member from the other. When I try to basically separate those two members, I have two types of failure mechanisms. If this point side penetration is very small, I will get simply a withdrawal of the point of the nail. However, if this head here is very small, what can happen is that I have a kind of punching, so crushing of wood at the interface with the head. I don't know if this is clear. If the head is very small, the head can indent the wood. So I can have that this head is going inside here. I mean, it's not this going inside. This member here goes outside. If this is very small, this is going to indent the wood. Two different failure mechanisms. So in two formulas here, one is for the first failure mechanism, the other one is for the second failure mechanism. And then of course you see we need to know the length of the points of the nail, T-pen, and also the diameter of the nail and the diameter of the head. And then we need to know how to estimate this characteristic point side withdrawal strength, characteristic head side pull through strength. This is for nails other than smooth nails. For smooth nails, we have this other slightly different relationship. The regulation says that this value F(AXK) and F(head_K) should be provided by the nail producer. So once you purchase the nail from a certain producer, for example in Italy we have Rotoglass, which is very famous, they will provide you with a handbook. In this handbook, you will find all these properties that were determined based on experimental testing that they did in some laboratory. The regulation, however, for smooth nails with a point side penetration of at least 12T provides this kind of, again, semi-empirical relationship to calculate F(AXK) and F(head_K), depending, as usual, on the characteristic value of the density. Last thing, and then we finish. What happens if your nail is subjected to combine laterally and axially forces? In this case, you see, for smooth nails, we use a linear interaction criteria. So we do the ratio between the axial force demand and the axial strength. And we sum to this ratio the ratio between the shear force demand and the shear strength using Johansen equation. The sum shall not exceed 1. Instead, if you have rib shank nails, then those ratios are taken to the power of 2. So we use a circular or quadratic interaction criteria. Okay? In this way, this could be the case, if you remember, we saw last time, where you have a connection like this, plate, you have a beam, and here you have a nail. So in this nail, so this is the force of the beam, this is another member, so this nail is subjected to axial force due to this bending moment, and also to shear. In this case, since you have both axial force and shear, if you have a smooth nail, then you have to use this linear interaction criteria. If you have a ring shank nail, so nails with some more friction, you have to use this other interaction criteria. Okay, any question about what we saw today?
La differenza tra i due, cioè
Okay, the difference between the two members, if you want I can tell you in Italian, this is not clear. If you have
Qual è lo sfilamento oppure
allora, o lo sfilamento o il punzonamento della testa, ok? O lo sfilamento del chiodo, andiamo dietro, o lo sfilamento del chiodo da questo elemento, oppure il punzonamento della testa dell'altro elemento, ok?
no, la dipendenza dal diametro, cioè la dipendenza dal diametro dell'uno e l'altro?
No, no, la dipendenza del diametro non c'è qua. Non mi ricordo.
Ma c'è nel passo di dire che c'è qualche parametro che vogliamo di differenza che era
No, qua vabbè, qua c'è il diametro, il diametro sì, diametro del chiodo, diametro della testa, lunghezza della punta e basta, e poi c'è questi valori di resistenza specifica che generalmente vengono forniti dal produttore, oppure in questo caso li potete calcolare con queste formule semi-empiriche. Ok.